And now it is time to move along to our keynote speaker, and I'd like to bring him out on stage. Just a short introduction before I do so. Steve Douglass is Lattice Semiconductor's Corporate Vice President of Research and Development. He joined Lattice in September 2018, and he is responsible for the development of all hardware, of all software and solution products for the company. Steve has over 30 years of broad technology experience developing programmable solutions, so we can't wait to hear what he has to say. These solutions are for many markets, including wired and wireless communications, industrial, there's automotive as well in his repertoire, and test and measurement. Now, his presentation is titled Embracing Change, the Mandate for Success in the Next Generation of Embedded Design. And in this presentation, he will be exploring together with all of us the concept of adaptability in embedded engineering, including the related trends making increased adaptability essential, the emerging and existing applications that require adaptability, and the types of technologies helping engineers future-proof their designs with adaptability as a core guiding principle. All right, now it's time for us to bring him out. It's high time. Please give a very warm round of applause for Steve Douglass.
Thank you so much.
Thank you. The stage is yours.
For that very warm welcome, and appreciate it, and great opportunity to be here at Embedded World. And thank all of you for being here today. Welcome to day 2. I got to tell you, it is so exciting to be here in person and to see everybody face to face. This is my first travel out of the United States in the last 2 years, so very exciting times. And also very grateful for the streaming technology, the ability to share this live with all of our friends around the world that weren't able to join us here in person. So they too can be part of this great event. So today, I'm very honored to be here on behalf of Lattice Semiconductor to talk to you about some of the exciting and major trends that are going on in technology in the industry today. But these are trends that are causing us to pause and rethink our approach to embedded system design. They're compelling us to include more flexibility and adaptability in our designs so that we can capitalize on these new technologies and continue to accelerate innovation at the edge. So let's talk connecting literally every device on the planet to the internet. Not just cell phones and laptops and servers in the data center, but everything else. We've got factory equipment, we've got cars, we even have our household appliances all connected. This year, by the end of the year, we will have about 15 billion devices connected to the internet. And that number is expected to double to 30 billion in just a few years. Those are a lot of devices connected to the internet. And all of these devices are being equipped with sensors to observe their surroundings and to understand the environment that they're operating in. The most popular sensor that we're arming them with are cameras and video sensors, but there's also audio sensors, microphones, radar, LiDAR, accelerometers. And all of these sensors are gathering tons and tons of data. IoT devices alone, by 2025, are going to generate 80 zettabytes of data. That's 80 zettabytes. I had to look it up. What the heck's a zettabyte? It's a trillion gigabytes. That's a ton of data, 10 to the 21st bytes. And all this data typically has been processed in the cloud. We gather the data on the edge, we send it to the cloud and do all the heavy compute. But there's another trend emerging, which is the integration of intelligence in all of these edge devices. These edge devices are getting smarter and smarter every year. We're integrating more advanced artificial intelligence. And these algorithms are very data intensive, and they need to be processing information, analyzing it, and making real-time decisions. And oftentimes, there isn't time to go to the cloud and back. We can't handle that latency. And so a lot more of the data is being processed with these smart devices on the edge. So it's a lot of exciting technology. It's presenting a lot of opportunity on how we can advance our system designs. But it's also creating a lot of challenges to embedded designers. Or, like we like to say in management, opportunities. These opportunities are manyfold. First of all, we talked about all this large data that's being generated across all of the devices on the internet. All of this data has to be processed in a very timely fashion, many applications needing it done right there on the device itself. Take, for example, today's modern car equipped with ADAS. It generates 25 gigabytes of data an hour, and that's expected to accelerate to over a terabyte an hour. And this data has to be processed, analyzed on time, all the time, for safe operation of the vehicle. And so localized compute is very important. And it's not just extra compute we need. It has to be power efficient. Because all of you are designing for devices on the edge, you know that edge devices are often in very harsh environments. You can't get good air cooling. There are very stringent heat dissipation and power dissipation requirements. And many times they have to be in very small form factors. And so these devices are going to need a lot more compute, but it has to be very power efficient. And all of this intelligence that we're adding to devices, these AI algorithms, they're changing very rapidly. Seems like every other day there's another neural network that's out on the scene. So just when you think you have the optimal solution for your device, another AI solution comes along. And this is really driving the need to more rapidly expand the features of our systems. We really need to do more refreshes of our devices and have updates that are taking advantage of all of these new capabilities. Now, one other challenge that we have to face is one of increased security threats. We talked about we have this wonderful, fully connected world, and we can access all the devices we deployed around the world. That's great that we have access, but so does everybody else, including the bad actors. And I'm not just talking about security threats in the data center, where our personal information seems to be compromised at an alarming rate. It's also out on the edge, too. If you look at cyber attacks on cars are up 225% in just the last few years. Cars getting hacked, right? And there's a lot of critical infrastructure that's now internet enabled. This infrastructure is also at risk of an attack. In the United States last year, the Colonial Pipeline, which services the entire southeast of the country with gasoline and jet fuel, was brought down by hackers with ransomware, shut down the pipeline, and caused a state of emergency for several hours and wreaked a lot of havoc. These are just a couple of examples of the type of security threats that we face on the edge because we are now such a wonderfully connected world. So with all this accelerating technology capability coming our way and all of these advancing and evolving threats coming, it's becoming paramount for us to do product updates more often, but they need to be done in a cost-effective way. We can't always redesign from the ground up and redeploy. It's very expensive, very time-consuming. Time to market is becoming more important than ever before. And I know not all embedded markets are really that time-sensitive, but with all these technology trends, I think that's changing, and we're seeing a lot more pressure with time to market. So every one of these challenges that we're facing, they're pointing for the need to have more adaptability in our systems. The ability to respond to all of these changes, all these opportunities for new technology, all these new security threats, and to update our systems and modify them real time without having to do a massive redeployment. So what are the ways that we can introduce adaptability into an embedded system? Well, let's look at what an embedded system looks like. This is a grand oversimplification, but I think it shows all of the key elements that are in an embedded design. There are hardware and software layers in every system. On the hardware side, we have a physical hardware layer that connects the device electrically to the rest of the system and the world around it. And there's a logical layer for implementing processing units like CPUs and MCUs and all of their peripherals. And then on the software side, there's system software that makes the hardware visible to the software programmer, and then the application software runs on top of that, and that's where all the features and capability of the system get introduced and deployed. Now, software by its very nature is very flexible. It's very easy to just update software. You recompile code, get a new binary, and away you go. It's as simple as that, right? Software is really easy. Spoken as a true hardware guy. It's always easier when someone else has to do all the work. But seriously, software introduces a lot of flexibility into our embedded systems. But if we can add flexibility into the hardware layers, that would give us the ultimate adaptability and give us the most flexibility to design our systems to adapt to the changing world around us. So let's explore some of the ways that we can add system adaptability with both software and hardware. So I think we're all very familiar with, as I just mentioned, the relative ease at which we can update system capability and features and performance with a software upgrade. All you have to do, update the program, reload it into the system, and away you go. Now, in ancient times when I was a design engineer, that was done with a little device called a floppy disk. And you slipped it into the drive and you downloaded that into the memory of the computer. Well, thank heaven for the cloud. It's a lot simpler than that. You can oftentimes get the software updated very easily. Just pull out your iPhone and you see that little red dot that said you have 17 new applications that need to be updated. With a click of a button, update all. A little patience, in a matter of minutes, you're now equipped with all kinds of new capability and features and performance on those applications running on your phone. Now, the cloud also gives another very important element of adaptability to our systems, and that's the ability to scale software performance by offloading some of the compute requirements to the cloud. A lot of times, local systems only have a finite amount of compute resource. They can only run so much software locally, so why not offload a lot of that work, all the heavy lifting, up to the cloud, where there's a lot more compute capability, a lot of heavy calculating equipment up there. You can really do a lot more in the cloud. So those are two different ways that you can do system adaptability through software. Downloading updates to the local device and uploading more work for the cloud to do for you. So software adaptability is really, very key to our ability to update our systems. Now, one of the problems, though, with relying just on software adaptability is this growing requirement for more compute performance on the edge of the devices, especially the compute requirements of AI algorithms. AI algorithms are very data intensive and they require a lot of compute, and this is a huge shift in the market as of recent. As you look at the graph here, AI algorithms have been around for a long time. And for several decades, they progressed very nicely at Moore's Law, doubling their compute requirements every 2 years. Moore's Law was a nice steady beat for the hardware side too, so it worked out really nice and harmoniously. Well, about 10 years ago, with the advent of the deep neural network, and when AlexNet burst onto the scene, it was a tectonic shift in the evolution of neural networks and the implementation of machine learning algorithms. The number of neural networks has exploded. As I mentioned, it seems like every few days there's a new neural network algorithm that's out there. And not only are there significantly more algorithms, the compute requirements of these are dramatically higher. There's a lot more layers of processing of the data as you go through the neural network. And they're basically doubling every 3.5 months the compute requirements for these neural networks. That's 7 times faster than Moore's Law. That is a very sharp clip of acceleration in the performance requirements. Now, at the very same time, CPUs and processing units are running out of gas. They can't even keep up with Moore's Law anymore. I think we've all, seen the progression of this. Mainstream CPUs hit the power limits several years ago, and once they hit the power wall, all they could do is rely on some process technology scaling and pipelining and other innovations to try to get the frequency of the processor to go faster. That ran out of steam. Then they went to multi-core. Even multi-cores have a diminishing capability to add extra performance to the system. There's no way that CPUs can keep up with this alarming increase in the amount of computation that neural networks need. So it's really paramount in this new paradigm that we shift from a CPU-centric compute model to a heterogeneous compute model where the processor has at its disposal many hardware accelerators that do very dedicated functions and offload a lot of this heavy compute from the processor. There are a lot of different options for hardware accelerators out there today. So in this particular chart, I'm just showing a nice comparison here of the performance gains that you get versus the hardware flexibility. As we talked about, MCUs and CPUs, you can have multi-core, and you can do pipelining and multi-threading, and you get some amount of performance gain, but you just can't keep pace. Now, there are a lot of ASICs and ASSPs out there that are building SoC architectures that are leveraging this heterogeneous compute model. They do have a central CPU, and then they have multiple hardware accelerators where these heavy compute functions are offloaded, like video signal processing, DSP, AI algorithms in particular. This is really great because you get a lot increase in performance on your system, at least for the application that they're targeting. Now, one of the downsides with ASICs and ASSPs is once you design it and you choose your hardware accelerators, the performance is fixed and you're stuck. That's all you get. And then as the algorithms advance, particularly in AI, and you need faster accelerators, you can't get it unless you redesign the hardware. And we all know that ASIC development costs are growing exponentially, and the time to develop them is prohibitively long. So that's a huge disadvantage of those solutions. They're great if you don't have rapidly changing requirements, but if you do need to make a change, it's a long road to hoe. Another option are GPUs. GPUs are massively parallel. They have hundreds of cores that all operate in parallel on the same instruction. So there are a lot of applications where you need to do the same computation a lot of times, and you can do it all in parallel and get there a lot faster. So that's why GPUs are very popular in many applications. In fact, AI network training done in the cloud is usually handled by GPUs. On the edge, though, it's a little more challenging because GPUs can be pretty power hungry. They can draw up to 100 milliwatts. There's also another limitation on the flexibility. All those hundreds of cores are all executing the same instruction at the same time. So if you have diversity in what you're trying to compute simultaneously, you really can't do that. There's a level of sequential performance challenge for the GPUs as well. Not quite as restrictive as a CPU and the traditional von Neumann architecture, but there are some limitations on the flexibility. Another option is the Fpga. And Fpga is also massively parallel. It has the ability to implement all kinds of independent functions as well, too. You can have multiple hardware accelerators doing different things operating in tandem at the same time. And they're also very power efficient. And because they're programmable, you can tailor the implementation of the hardware accelerator or the AI engine to exactly what you need. If you don't need the full-on neural network and you want to skip a couple layers or you want to prune the network, you can build exactly what you need with a trimmed network in the Fpga. And the beauty of the Fpga is you can modify that design later. If the requirements of your accelerator change over time, you can modify the design in the Fpga. Let's take a little bit closer look at the architecture of the Fpga and what's enabling that extra hardware flexibility that's so valuable. At the heart of the Fpga architecture is a programmable core. It's a core of lookup tables and programmable interconnect that allow you to implement virtually any logical function that you want to in that fabric. And interwoven in this core of programmable logic are configurable DSP and memory blocks as well. And so the combination of these creates a very tightly integrated, power-efficient compute fabric that allows you to implement hardware accelerators very efficiently, especially AI engines and machine learning algorithms that are very heavily dependent on doing lots of matrix multiplies. So a lot of configurability and flexibility in the core, and FPGAs also have configurable I/O, both parallel and serial or SerDes. There are a lot of different protocols and industry standards that are rapidly changing over time. The FPGA allows you to reconfigure and reprogram the I/O interfaces, giving you another degree of flexibility to adapt to change in your design. And this is probably the most exciting thing for me and the most important point of my entire keynote. So if you don't remember anything else, this is the point. FPGAs can be field upgraded. They can be reprogrammed after they've been deployed out in the field. And you can do an update to an FPGA with the same relative ease that you can do a software update for application software running on a CPU. You have to redesign the code in RTL and recompile it, but you generate a binary bit stream and download it over the cloud, and it gives you a whole new set of hardware functionality without ever having to touch or change the hardware. So imagine this. You have very flexible and adaptable software through software updates, and now you can update hardware with the same flexibility and relative ease. So FPGAs probably give the most flexibility for adapting to change in the hardware layers of the system. Say, okay, Steve, that's great. FPGAs are very flexible, but aren't they really big and power hungry, like those GPUs that you were talking about? Well, yes, there are FPGAs that are very large and very high performance and very power hungry, but those are really focused on hardware acceleration in the data center and doing a lot of complex compute functions and communications heavy iron infrastructure. There are also a lot of other FPGAs out on the market besides those big giant FPGAs. And these are much more suited for embedded design. There are a whole host of mid-range FPGAs that are targeted towards delivering optimized performance. So all that extra compute that you need to add to the systems that I talked about, mid-range FPGAs helps you deliver that capability. And there are also very small FPGAs that are power optimized as well. We don't need a whole lot of compute, but just need a little programmability in your hardware. We actually have at Lattice FPGAs as small as less than 1.5 millimeters on a side. So no matter what your edge application is, there is an FPGA out there that's optimal for your design. So now that I've talked about how we can add adaptability to the system with both software and hardware, I'd like to explore how we can use this adaptability and apply it to several applications in the industry, and allow them to capitalize on a lot of this flexibility that we've been talking about from these new technology trends. Let's take, for example, in-cabin AI systems. These systems were created and were really focused on driver monitoring when they first came out, making sure the driver's not nodding off at the wheel or looking out the window in the wrong direction and not paying attention to the road in front of them. In fact, several years ago, I was on a business trip. I flew into Munich, and I had to drive to Austria at night. I had a car that had one of these systems, and there was something wrong with the GPS, and I kept looking over at the map. And if I stared at it for more than 2 seconds, the darn thing would start beeping and flashing at me. So I didn't really disable it, but I just kind of ignored it. But seriously, these systems now have really expanded in their capability. There are now a lot of capabilities for operating in-cabin systems like your radio. There's a lot of gesture detection AI that's been integrated, so doing little hand signals to turn your radio on and off, crank up the volume, turn it back down. There's also things for operating your GPS hands-free. And all these new features and capabilities and experiences in the cabin are being fueled by a lot more AI algorithms that are very compute intensive. And so obviously you need to do a lot of software updates to enable all this capability, but you also need to have a lot of hardware acceleration. And I think in-cabin is a good example of one of those harsh environments. You really don't have a lot of good air cooling. These systems are often mounted in strange places like behind the mirror, the rearview mirror, or somewhere embedded in your dash. And so they really need to be very power efficient. So the FPGA is often a very good choice for implementing the flexible hardware portion of the system. So AI capability is expanding in in-cabin systems through both software adaptability, through software downloads through the cloud, as well as through FPGA-enabled hardware flexibility. Another example system from the commercial world is the smart doorbell. These are clever little doorbells with a camera in it, so they can watch out for the porch pirates trying to steal the latest package that was put on your porch while you were away at work. These devices have typically, when they first came out, they had microcontrollers that were processing all that image coming in, doing some basic AI like human presence detection, but a lot of the analysis was really, the data was shipped off to the cloud, and it was done remotely in the cloud, and then the information came back. So this is a really good example of how software offload to the cloud can give you that extra flexibility. Now, over time, there's been a lot more capability added, embedded, camera resolutions get more advanced, and there's need for more elaborate processing of the signals coming in and the images. And so FPGAs have actually become the device of choice for the hardware because they're a lot more power efficient for doing those AI algorithms than the microcontrollers trying to do it all in software. And it's also given the flexibility to update the systems over time. So a couple of great examples of how both software and hardware adaptability are enabling the advancement of integrating AI at the edge. Now let's talk about a couple of examples in embedded vision. There are a lot of integrated cameras and video devices out there in the world. One of the really cool ones that I like are autonomous mobile robots, or AMRs. These robots are working very diligently in a lot of different industrial applications. One of the most common ones is zipping up and down along the warehouse, pulling the packages for all the online orders that are happening today, especially while we were all locked up for 2 years and couldn't get to the store to go buy anything. These AMRs, they have a lot of sensors on them. They have obviously the cameras, but they also have audio sensors, accelerometers, and there's a whole bunch of data that's being generated because they're in a very a very unique environment where they need to be aware of all of their surroundings as well as where they're located. So they have a lot of very intense algorithms that are called simultaneous localization and mapping. And that's basically an algorithm where the robot maps out the entire area that they're in and then their precise location, as well as any other obstructions that are potentially around them. There's also a lot of advanced AI for doing collision avoidance because you don't want that robot zipping down the aisle, crashing into another robot, or worse yet, some employee wandering along the factory floor that was on break and didn't really pay attention to the fact that the robots are there. So there's a lot of heavy, intense computation that needs to happen on these robots, and there really is no time to wait for the results to come from the cloud and back. So the software has to be local, and there's a lot of computation, so you really need to have hardware acceleration as well. And the hardware acceleration can be done with ASICs, ASSPs, GPUs, FPGAs. Any of those choices are an option. But again, depending on the design and depending on how much future-proofing you want to have, FPGA can really be a good choice for implementing the hardware acceleration. So in that particular example, software updates and hardware acceleration, both very key to driving adaptability. Another application is machine vision cameras. These are often used in a manufacturing environment where you have product going down the line and you want to inspect it and look for defects. And so as depending on where you're at in the processing of the equipment and the type of equipment that you're looking at, the type of defects will vary. And so the information for the image patterns that you're looking for often need to be updated or refreshed and modified. And so software updates are very critical for keeping machine vision cameras fully equipped with the latest information that they need. Now, oftentimes, software is sufficient for doing all of the image capture and all the signal processing, and so it really is sufficient to have software updating for lower resolution cameras. But for higher resolution cameras like 4K resolution and above, and if you have a lot more intense ISP calculations to do, it really is a good idea to have a little bit of hardware acceleration capability there with the FPGA for the ISP. And as you migrate to different types of sensors in your system, this is an example of where some of the protocols and the interfaces are changing. So you get a lot more flexibility to update your hardware design a lot more quickly with an FPGA so that you can change it and adapt it to these changing interconnect standards. So just a couple of good examples of how software and hardware adaptability can be applied to have perpetually improving and advancing technology in embedded vision systems. Now let's talk about that security problem that we talked about. There is a huge need to have adaptable security solutions. As we talked about, there's growing cybersecurity threats on the edge, and as edge systems get more complex, the attack surface for these cyber attacks becomes larger. You heard yesterday about software-defined cars and all the great technology that's going in those devices. Well, today's modern car has like 100 ECUs in it. Each one of those devices can be a target for a cyber attack because each one of these is operating from firmware that can be hijacked if you don't have the proper security in your system. And so the attack surfaces are getting larger, and the ways in which the attacks can happen, the attack vectors, is also increasing. And so it's never been more important and imperative that we keep our software security updated. We've got to keep the firewalls updated, all the intrusion detection algorithms. You've got to keep the software, security software updated on your system. But it's not just software security alone that we need. We've got to have hardware security too. And some of the hardware security can only be done with hardware. It can't be done with software. You've got to have a hardware root of trust to boot your system. A device that you know, you're confident 100% has not been compromised anywhere in the manufacturing of the device to the deployment of the device that can reliably boot your system. Now, there are a lot of hardware root of trust devices out there today. There are ASICs and ASSPs. There are even microcontrollers that can be used for the hardware root of trust. And that's great because those can be built into your system. The challenge is they're all based on cryptographic algorithms that are changing with time. The attacks are getting more elaborate. They're getting more sophisticated, and you've got to have more sophisticated algorithms to combat that. You've got to constantly advance your cryptographic algorithms. And so the problem is, if you do a hardware root of trust with an ASIC or ASSP or a microcontroller, is your cryptographic algorithms are chosen, and you're frozen in time. You cannot advance those algorithms unless you advance to the next release of the hardware. With the Fpga, though, you have the flexibility to update those algorithms real time. And it's important that we do so because, like I said, these attacks are changing at a very rapid clip. In fact, one of the biggest threats in front of us for cybersecurity attacks is the result of another brand new and exciting technology coming our way called quantum computing. Quantum computing, if you take the Google quantum computer as an example, it can do calculation in 4 minutes of what it would take supercomputers today 10,000 years to compute. That's 150 million times faster computation. That's really great when you're applying it for a lot of important calculations that are for the good of mankind. However, if you're a bad actor and you're trying to crack a security code or an encryption algorithm, you can get to the answer a heck of a lot faster. So we need a lot more advanced algorithms to combat that. And having FPGAs where you can refresh those hardware cryptographic algorithms a lot more quickly gives you the tools that you need. That, combined with the software updates, are really the only way that we can stay ahead of these escalating cyber attacks. Okay. Talked about how we can apply adaptability to a lot of those key challenges that we talked about. Another one that we haven't really talked about yet is time to market. And we all know that as much as I'd like to say FPGAs are really easy to design with, it's not quite as fast and easy as compiling C code to run on a processor. So to help our customers to be more efficient and get their products to market more quickly, we are very focused on delivering them solutions that really accelerate their development and integration of these adaptable features. We have a whole host of embedded FPGA and embedded design tools for implementing the design, and we have pre-engineered software and hardware IP that customers can use as building blocks and reference designs for implementing these adaptable solutions. And we've created solution stacks of all of these elements that are focused on several of these key challenge areas that we've been talking about. We have a solution stack for implementing AI on the edge. We have an embedded vision solution stack, and we have them for security as well as industrial automation. So all the exciting trends and challenges people are facing, we're providing them solutions to help them integrate that more quickly. And it's not just our software and our solutions that we're advancing. As you can see from this nice fancy graphic from our marketing department, that our hardware portfolio is also expanding to provide more options for that hardware flexibility. Our industry-leading power-efficient Nexus architecture for small FPGAs. That platform has been leveraged to deliver 5 different FPGA families. And we are also on the cusp of launching a brand new platform called Avant for the mid-range. Avant basically takes our power-efficient leadership from the small FPGAs and scales it to 5 times the logic capacity. And they have a lot more compute capability and I/O bandwidth that allow customers to implement a lot more of that very critical edge compute capability that are needed in today's modern embedded system designs. So we're very excited to be announcing this product. It'll be launching later this year. So stay tuned. A lot of great FPGA technology coming with Avant. Okay, so in closing, we are in a very exciting time in our industry today. Probably one of the most exciting times I've ever seen in my 35 years of experience, probably more if you count accurately. But there's a lot of rapid change going on. And these are very tectonic changes. And in some ways, these changes mirror all of the huge disruptive changes that went on in our personal lives over the last couple of years as we all navigated a worldwide pandemic. That's a little ironic because the embedded world is where technology intersects our personal lives. Well, just as we had to change, we had to adapt to this new world order and change the way we go about our lives to not only survive but to thrive, our embedded designs need to do the same going forward. We've got to make our systems more flexible and more adaptable so that they can leverage all this great new technology coming their way, and they have the ability to thwart these new and growing security threats that are coming our way. So adaptable system design is no longer a luxury, a nice to have, something that you can use to differentiate. It's imperative for success at the edge. And at Lattice, we are very committed to delivering you all the hardware and software systems that you need to be successful in implementing adaptable systems. So with that, I'd like to say thank you very much. If you want to hear more about adaptable embedded systems, come visit us at our booth in Hall 4. We got a lot of great partner demos that are demonstrating this adaptability in action, as I like to say. And with that, I'd like to say thank you very much and enjoy the rest of the conference.